So I'm going to start with the demonstration that we've done previously, and that's, of course, in the picture. Whoa. All right. So a little psychedelic there. We have our 5-gallon water container. And what we're going to do is we're going to try to crush that, making a partial vacuum. So we did this early in the year, but I'm going to revisit that demonstration. So I'm going to start with some methanol. All right. And all I'm going to do is add a little bit of methanol into the container. I'm going to increase the surface area. It's going to feel what temperature? Cold, because evaporation is an endothermic process. And I'm trying to get all these vapors into the gas phase. So the heat of vaporization of ethanol took energy from its environment. Evaporation is an endothermic process, and I'm just getting rid of the extra here. And what I hopefully have is a flask or a container filled of methanol vapors. Okay? And of course, there's already oxygen in there. So all I want to do now is make it react and collide with the oxygen. So I'm going to use a little sparker, a little bit of activation energy. Not sure if we're seeing that, but that's what should ignite my alcohol vapors. All right, and hopefully we get a good reaction. Now, it's not the reaction I care about, although if you remember, we're going from something unstable with high energy in its chemical bonds, high potential energy, and when this gives off energy, it becomes what? Becomes stable or unstable? Stable! CO2 and water are products of combustion. So let's try this. Okay, it can be a little loud at times. It's not what I'm going to do initially, it's what I'm going to do right after the reaction. That counts. So ready? 1, 2, 3. And of course, same problem I had earlier today. 1, 2, 3. All right, we're going to have to go with a match. Okay. Sometimes that sparker doesn't work. And let's go with a match. Here we go. So again, 1, 2, 3. Hold your ears. Sometimes it's louder than others. But I capped it, and what happens? What crushed the can? Or in this case, what crushed the bottle? Atmospheric pressure did, because what did I do to the pressure inside? I lowered it by doing what? I increased the temperature, which did what to the gas inside here? What happened to the volume when temperature goes up? If it make a gas go faster, does it need more space? If a gas is moving faster, temperature is motion, does it need more space? So it expanded out of the bottle. The remaining gas that was in here was enough to keep the bottle from imploding because it was going faster than the gas outside. But as soon as I capped this, and the fire went out because there was a lack of oxygen, then the remaining gas got cooler. And as the temperature dropped, what happened to the pressure inside? Decreased. There wasn't enough molecules in here to keep the collisions up to the outside, and I crushed the can. Of course, if I pop the top off, what's going to happen?
It's going to go back.
Air is going to rush out or in? In. High pressure to low pressure. So, okay, not perfect because it's not. But some have rushed back in. This is pretty much done. Another way to crush a can, all right, if I take a solution, an ice water solution, which I don't have the water, so I'll add some. So I have an ice bath here. Of course, when you pour like your cooking show, you go up and down. Okay, so I have an ice bath. Now what I have cooking here are some cans. These cans have water in them, so water's boiling. The top is open. All right, now the top being open, I'll just use the glove. Top being open, gas is coming out of these cans. What I'm going to do is take these cans that are boiling hot water, the gas is expanding, and I'm going to do the same thing. See if you can watch what happens. So I'm going to take this can, very hot. I'm going to invert it. Watch carefully. What just happened to the can? It was crushed. Why? Same reason as the other can was crushed. Who crushed it? Atmospheric pressure. Here we go with another one. Okay, let me grab it from the bottom. By inverting it, I'm closing the top, aren't I? Kind of like what I just did before. And this one doesn't want to work because I didn't have enough water. Let's sit there in the hot water. All the water evaporated out of that. Need some more water. Let's take it hot. Okay. Now, I can do it without heat because these last two problems I started with high temperatures. What if I do it another way? I'm not even going to heat it. All right? Not even going to heat this. I'm going to turn it like this. That's its sexier side. Okay? Okay? All right, now, so it's my so what I'm going to do now, instead of heating this, notice the top is on. Okay? I am going to just pour some liquid nitrogen on it. What's going to happen there? What's going to happen to the pressure inside as temperature decreases? Right, so what should happen? Well, listen carefully as we go here. What's that sound? That sound is the sound of what, you think? Look carefully. What's happened to my can? You see it bending in? Yeah. Atmospheric pressure is crushing this can. Because as the temperature drops, what's happening to the pressure in this can? It's decreasing in atmospheric pressure. As temperature drops, the molecules speed up. Can you see what's happening on the back side here? On the wrong side showing. I thought that was the sexy side. It's making it really cold. And you can see that atmospheric pressure, okay, is crushing this can. Because the gas inside is now moving so slow, it flipped over for you. All right, so you can clearly see this nice pressure. Okay, this can, woo, cold. Okay, I'm showing the wrong side. Nice and crushed. Now, would it have worked if the top was on? Off. What the demonstration I first showed you, where I capped the bottle, would that have worked? No, on the plastic bottle. Why did I invert the can that got crushed? So that it was covered. And why do I want to cover these openings? What did I want to keep constant inside these containers in order for this relationship to work? It was temperature pressure, temperature volume, okay? What has to stay constant? That's why I capped them. I inverted this one, I kept this one capped, and I capped the other. I had to make sure the moles stayed constant, because if they did not, party people, this wouldn't work. So pretty fantastic crushing by atmospheric pressure just by dropping the temperature. The others came with heat. Lower the temperature, what? Lower the pressure. The other ones I did what? I first heated them to expand the gases, and then they got cooled, either by the ice bath or by just the fire going out. Temperature-pressure relationship. Okay, that's really cool. All right. All right, now, another demo for you. And this is what we're going to study today, a little bit. I got my vacuum chamber back up. Let's get up close and personal. Right into the first date space. All right. Okay, picture of a picture of a picture. All right, now, in this demonstration, I'm going to take a vacuum chamber and I'm going to take out holes of gas. Okay, remember this thing really does what? This thing really what? Sucks, all right? So, before I put this on, I'm going to attach it here, and I am going to add, now we did, what, marshmallows the other day? And marshmallows are a colloid because They're actually gas trapped in a solid. I'm going to give you another colloid. This one is a gas trapped in a liquid. Does anyone know what a gas trapped in a liquid is called? You just had Halloween. Some people like to use it. All right. What is the gas trapped in a liquid called? When we go to the beach, this is West Hampton Beach. What do we see when the waves crash and the air gets trapped by the waves? You see what? Foam. Okay, foam, yeah. The bubbles get trapped in a liquid. So we're going to use some shaving cream, which is an example of air trapped in a gas. So I'm going to take this air trapped, in a liquid, and I'm going to try to fill this up here. Hopefully I have enough. This looks like it's hurting. Do I have a fresher or a better container? I don't know. It's going to work, I guess. All right, it doesn't look like there's a lot of there, but let's see if I have a fresher shaving cream, because over time the gas does come out. But we'll try it. That looks pretty lame to me. Ah, thank you. This is foamier. Okay, that looks pretty lame. Oh, now we're talking. Oh, yeah. Shaving cream. Okay, so we got a beaker filled with shaving cream. Now that represents, a liquid, gas trapped in a liquid. And the size of the volume of that gas is what makes the cream foamy, the size of it. I'm going to take out gas molecules. By taking out the gas molecules, what's going to happen to the pressure on top of that gas trying to keep its volume? As the pressure decreases, because I'm taking out gas molecules, what happens to the volume of space? Increases. What kind of relationship is that? Indirect or inverse. So let's just do it. Okay, stop talking about it. Whoa! So yeah, that really expanded. Now, I don't know if you heard the commercials, but this is your brain. This is your brain on drugs. Okay, so now it's a mess. All right, extra credit time. All right, let's take a cat.